Thank you for, I would like to thank the organizers for inviting me. I have to say it's an honor for me and Philip to be here and celebrate Young's birthday. We met, of course, we met in also he was there. And then he left, leaving us very sad. We missed the conversations and his presence there. And also, we learned to appreciate his wide view, his very extensive view of mathematics. This is how far-reaching it could be and applications. I would like to add to the list of activities that Union has helped with here in Edinburgh, those in Korea. I mean, we were invited for 3 years or 4, I can't remember how many, to go to Korea, and we organized together with Union some conference there, and we were people from all over the place. And the common theme was a relationship between physics and mathematics. So this was very, very nice, and of course we enjoyed being in Korea very much. So thank you for inviting us, and now we will switch to my talk. So this talk, I think, goes very well with the title of this conference, right? So we will see precisely relations between.
You check all the boxes.
Absolutely.
Everyone.
So yes, so the aim is to illustrate, to give you an example of the rich connections between mathematics, in particular geometry and number theory, and theoretical physics. And in the example I will give you today is the physics of black holes in the context of string theory. So at the end of this talk, I mean, we'll end up with a fascinating identity, which relates the area of a black hole. I will tell you, this is a mathematical audience, so I will tell you later what that. The area of a black hole, right? It's a very physical object, right? And is given by L values, right? Basically, it's a formula in terms of L values, right? So how does that come about, right? So the left-hand side is proportional to what we call the black hole entropy, and it's a certain it demands a certain counting of black hole states. So it's a counting problem on the left-hand side, and then you're saying that you have a formula in terms of L values that gives you this area. So this is, to me, an extraordinary identity that we don't understand very well yet. So as you will see, this is associated to a Calabi-Yau and modularity on a Calabi-Yau and an L function associated to this Calabi. So this is work that was done with Philip, and the one I will focus on today, there is more on this, is the work that we did we finished it in 2019, in fact, with Philip and the then student in Oxford, Mohammed Elmi, now a postdoc in China, in Tsinghua University, and our algebraic geometer friend, colleague, Hugo and Stratton. So this picture was taken in Korea, in the market. I mean, we're enjoying the food there. So there is more about it since then, but I think it's very good to focus on one example that illustrates, I mean, the richness of these connections. So the plan is, first I will briefly review what the Calabi-Yau is, and you will see how they appear in the context of string theory and black holes. Then I will discuss the black hole physics. There is a mechanism to find black holes that called the attractor mechanism. This is in the context of this part will be very physicsy, so I hope it's not too torturous. Well, so I'll try to be but please do ask questions when I go. I will start talking about the arithmetic of Calabi-Yau varieties, so what I need about her to relate it to the black hole physics. So this part will be very well known for you, I think. So, and then I will put all together in the last section. Relate the black holes together. So what's a Calabi-Yau variety, right? So this will be the mathematical objects of interest. And these are, I'm going to focus on the three-dimensional, three complex dimension case. And these will be algebraic varieties that with certain special properties, right? So we define, we have defined the equations in an ambient space as we have the, can you see this, the mark? Yeah. So we have defined the equations in some ambient space. And of course you get some variety when you do that, but we have a variety that has some special properties, and those are typically encoded in the properties of this polynomial. Right. So at the moment I'm working over the complex numbers, right? So these are polynomials over the complex numbers. So Calabi-Yau manifolds are compact Kähler manifolds with vanishing first Chern class. Okay. So, but for us today, there is an equivalent definition, and is a theorem really, that there exists a unique up to a constant nowhere vanishing 3-0 form that I'm going to call capital omega, which is holomorphic, right? So this encodes the fact that the first Chern class vanishes, and I could state this for an n fold, right? But this I'm focusing on three complex dimensions. So this 3-0 form is holomorphic and is unique up to a constant, right? So what does that mean for the Hodge numbers of this is a complex manifold? What does it mean? It means that the dimension of H30, right? We look at the middle cohomology, H3, right? And this splits into type, like in this equation, right? H3 splits into type, PQ type. So what this means is that the dimension of H30 is 1. So this Hodge number is always 1. And the third Betti number, of course, is the sum of 1 plus H2, H21, H12 plus 1 again, right?
Are you assuming that H1 is 0?
HB1.
No, H1 0. No holomorph.
Yes. We're assuming that H1 0. I will assume that, yes. So the third Betti number is twice 1 plus H21, right? And H21, so that means that this Hodge number, in general, which wouldn't be topological, is not topological. And it's a very important number in the context of the geometry of Calabi-Yau manifolds, right? In fact, it counts the number of complex structure deformations, right? So I'll come to that in a moment. So Calabi-Yau varieties have parameters, right? So I'm going to denote them generically with the complex structure. I'm going to denote it by a phi here, and we have H21 of them, right? This is a Kähler manifold, so it has a symplectic form that is right. So it also has a Kähler structure, right? And those are counted by the second Betti number, because I am assuming that H21 to 0 is 0. So the moduli spaces of Calabi-Yau manifold have very interesting geometry. I mean, it's also Kähler. For example, the geometry is called, a very good name, is called special geometry, but it encodes most of the physics that we associate with Calabi-Yau manifolds. I mean, for example, when we think about periods of the holomorphic tree form, those become homogeneous coordinates on the moduli space of the complex structure. But the periods also determine quite a bit of the physics, right? So that's a very important fact in relation to the black hole physics. We know there are millions of examples, right? Calabi-Yau manifolds by now. In fact, there are more than hundreds of millions. So as we have all heard about the quintic, right, before. So the quintic, the fact that we have a polynomial of degree 5, that is precisely the Calabi-Yau condition. Actually, it's an example of a quintic polynomial, and the x's are homogeneous coordinates before. Well, the example that we are going to focus on today is another one that is more complicated to describe. I will need toric methods, right? It's described as a hypersurface in a toric variety, and I don't want to do that. But there is a very beautiful fact in Calabi-Yau geometry that Calabi-Yaus come in pairs. They come in mirror pairs, right? And one of the statements in mirror symmetry is that this interchange the Hodge law. So H11 gets interchanged with H21. So it's very easy to describe the mirror of the hurricane barrel, whereas the original is hard. So what I will say today is that this example that was first written up by Helena Beryl in 1996, and then the hurricane barrel in 2005 wrote a beautiful paper about this example, precisely trying to describe some arithmetic properties of this case. So it is the mirror of a complete intersection Calabi-Yau, which is the product of three P1s with two polynomials that are linear on each. So this is what notation means. So yeah, so this has 5 Euler class parameters, in fact. So the mirror will have 5 complex structure parameters. So we take actually a quotient of that. So it's a rather complicated example, and I don't want to go into the details of that, but it is a well-defined. So this example is the one that will have very interesting arithmetic properties. And there are others, of course. Okay, any questions about Calabi-Yau manifold? That's all I need for the talk tonight. Are there any questions? Okay, so let me go to the physics part, right? So this is the attractor mechanism. So this mechanism of finding black holes in the concept of string theory was discovered by Ferrara, Kalush, and Strominger in 1995. And since then, there have been, hundreds of papers about this. There was one interesting paper for us today. There are many interesting papers, but for us, there was a paper by Greg Moore in 1998, where he made a number of conjectures about these black hole solutions that I'm going to describe. So this is where the inspiration for this work comes from, in fact, the paper by Greg Moore. So the physics it has associated to some superstring theory, right? That is supersymmetric, and we want to find black holes in this superstring theory. But for us today, I'm going to simplify this, and we're going to think about this as a 10-dimensional generalization of Einstein's equations for gravity, right? So together with Maxwell's equations for electromagnetism. Of course, this is a lie, right? The superstring is not just this. There's much more into the superstring theory. But this is what we need. So I want to take only what we need for this talk today, right? So this is what's important for us. So we're in 10 dimensions. We have Einstein's gravity in 10 dimensions together with some abelian gauge fields. Right? So the 10-dimensional space, the solution, the black hole solution, we mean in the 10-dimensional context of have 10-dimensional space-time, there will be a product more like a vibration effect, in which we have a 4-dimensional black hole, this 4-dimensional space-time, which is a spherically symmetric, asymptotically flat charged black hole parameterized by a radial coordinate r, right? It's spherically symmetric, so it's parameterized by the coordinate. I will say a little bit more about this. Times a Calabi-Yau manifold, a 3 complex Calabi-Yau manifold, to call X, with complex structure phi that depends on the point of the black hole, right? Depends on R. So this is at each point of the black hole. So that's the 10-dimensional space-time that we are going to consider. And the black hole, let me say a word about black holes, right? So the metric on a 4-dimensional, will have to be the metric of a 4-dimensional spherically symmetric asymptotically flat black hole, right? So this is a spherically symmetric metric, right? The one that's written there, where t is time, right? The coordinate for time, x, y, and z are the coordinates for the 3 spatial dimensions. And and dx squared, if you forget this factor there, dx squared will be the Euclidean metric on space, on 3 space, right? And so the metric depends only on this function UR, right? And only on this radial coordinate. So asymptotically flat, means that at large distances, it looks like flat space, Minkowski space, right? So, so the condition, the constraint on U is that it goes to zero as R goes to infinity, and then you get your metric is dt squared plus dx squared. You took the flat minus dt squared. I forgot a minus here. Very important. Right. So you get minus dt squared plus the Lorentzian metric, right, in Minkowski space. So you get minus dt squared plus dx squared at long distances. But the reason it's called a black hole is what happens at r equals to zero, where we have a horizon, right? So this is not a singularity. It looks singular, but it's not. It's a coordinate. You can prove it's a coordinate singularity of the metric. And U tends to minus infinity in that surface. And you can think of this as the last surface, as a surface that separates the interior from the exterior of the black hole. And if you're sitting at infinity, is the last surface that you will see, right? So if you have people sending light in space along R, I mean, beyond R equals to zero, you don't see anything. The last surface that you see that is visible from infinity. Okay, so this summarizes what I just said, right? So we have a 10-dimensional spacetime where we have a Calabi-Yau that with complex structure that depends on the radius at each point of 4-dimensional spacetime, which is a black hole, right? So we have these lines here illustrate how so your Calabi-Yau might be deforming, might become singular, until we have a Calabi-Yau at the horizon. Right? Okay. So that's the metric. So this discusses space-time, what the space-time looks like, and with its metric, right? So the metric would be the gravitational field. So now we're going to discuss I said this is together with gauge fields, with abelian gauge fields. So this theory comes with U1 gauge fields. In fact, B3 of them, right? B3 is the third lucky number. So the black hole is charged, has charges, right? And the charges, I'm going to put them together in a vector, in an n of length B3, right? The Q's and the P's are the electric and magnetic charges. And in this physical theory, these charges must be integers, right? You cannot, they must be integers. So let me define a charge vector, right? So let alpha and beta be a simplistic basis on the third cohomology, right? This H3, right? And which this H3 with the three upstairs, I mean, this is the Poincare dual of the integer middle homology, right? So that's what it means. So we have a symplectic basis of H3, and I write a charge vector that in which the coefficients here are the charges. So we are looking for black hole, what we call black hole solutions, which preserve supersymmetry. And supersymmetry in physics terms, I don't want to go around about describing what supersymmetry is, but what it means for us is that it means constraints on the geometry, constrains your geometry of the solution, and it precisely gives, in particular, it gives you a set of equations, right, that constrains the geometry. And in this case, it gives you a first order differential set of equations for your function U in the metric and the complex structure of the Calabi-Yau, right? And these equations are called the attractor equations for a good reason. So these equations in particular represent a nonlinear dynamical system on the complex structure moduli space with flow parameter R1 over R. I won't write them because I don't want to distract with the details of that. So let me tell you what those equations say, right? So let me define this object, Z, this in physics is called the central charge, that is basically a period, right? Apart from the factor in front, this factor here, this here is a period of omega, and the cycle that is being used is the Poincare dual of the charge vector, right? And this object here is what's called the Kähler potential in the modular space, but it's a function of the periods. I mean, it's an object that depends on the periods of the Calabi-Yau. So what this equation says that given a choice of a charge of a charge vector, one can prove using the attractors equation that the complex structure parameters flow to a value, let's call it pi star, at the horizon, where the modulus of the central charge reaches a minimum. And it is independent of the starting value of at infinity, right? So this is a caricature of what is happening, right? So phi, the complex structure, is evolving smoothly to a fixed point, pi star, at r equals to 0. Right? Of course, to see it, I will have to give you the equations, and you have to use it from that. That is okay. So this is precisely what Ferrara, Karas, and Strominger did. And Greg Moore posed a number of conjectures on the arithmetic nature of the Calabi-Yau at the horizon. Like this Calabi-Yau, and I'm going to call this Calabi-Yau an attractor variety.
So is it,
Sorry, yes?
so it's a path in the moduli space
Yes.
of, say,
That's right.
23 folds or something,
For example.
or whatever Calabi.
The quintic won't work.
Is it smooth or is it
Yes,
singular?
yes, it evolves smoothly.
Okay.
That's right, yes. Yeah, of course you have to be,
And it itself is smooth.
which one?
Phi star, the limit.
That's a very important point. Yes, yes, because this point, this will be, as we will see later, is a smooth Calabi-Yau.
Okay.
Yes, I mean you can have, as I had in my picture before. I mean you could end up in a space that is not, but is. Actually, the singular cases usually happen when the minimum is 0. Right? So we are taking Z to be non-vanishing. If it vanishes, you end up in some singular space.
I think I asked you this before, but so this attractor equation, is it essentially just a supersymmetric Einstein equation?
It comes precisely from the supersymmetric, from the minding, by requiring that you have Einstein, but it's a supersymmetric version of that. In fact, that's right. This is why it's called supergravity.
With the electromagnetic charge.
Plus electromagnetic charges, that's right. So the attractor equations say more, right? They say that the complex structure at an attractor point is such that the charge vector doesn't have a 1-2 or 2-1 part. Right, is 0. So that's this is, and there is a very nice proof for this, but it requires special geometry. It's an exercise in special geometry. You start with this set of differential equations, and you can play with them using differential special geometry, and you end up showing that that you have this flow and that the charges have to satisfy this flow. Okay. So let me define. So we have attractor points, right? So they exist. I mean, there is a reason why. But let me start by defining what a rank 1 attractor is and a rank 2 attractor. So remember that as I started saying that we have a unique holomorphic freeform. This is this arrow in H3. And if I change the complex structure, that arrow will move inside H3 of Z, right? So now let me consider this plane. I'm going to call it VR of Y. It's a plane spanned over the reals by the real part of omega and the imaginary part of omega. Right, this is the blue plane illustrated there. So that plane, if I change the complex structure, that plane will move, right? Move inside that. So on the other hand, inside this inside H3, we have a lattice of vectors, right? Gamma, right? The image field Z. They're fixed, right? So I call a rank 1 attractor point a value of the complex structure such that this plane contains the line gamma. So in other words, if I choose a charge I move I vary the complex structure to see if we can coincide with that, if it coincides with that vector. So rank 2 attractor point on the other hand, you take more, you take 2 vectors, right? 2 vectors, 2 integral vectors that are in H30 plus H03, right? So now you have a plane spanned by those 2 vectors, and then you still have the plane defined by omega and omega bar. So as phi varies, this plane, right, moves, and at the rank 2 attractor point phi, the plane now coincides with the plane generated by lambda 1 and lambda 2. And these are very rare. It's very difficult to find a Calabi-Yau which has a rank 2 attractor points, and this is what we are going to focus on today. So at least intuitively, why is this so hard, right? So it's clear, it's a very obvious thing that if you have a line which passes through the origin, right, like in this picture, in general will not pass for another lattice point, right? Unless the slope is rational. Okay, so that's a almost trivial thing to say, but it's true. So it's not too hard to find a value of phi that such that coincides with this plane V, right? For rank 2 attractor points, we have a plane, and it is then much harder to find a price that coincides with the plane. So it's a much harder question. So there was always, I mean, since 1998, 1995, there was a question on whether this existed or not, right? The solutions of this type existed. So geometrically, what is happening, right, at the attractor point? So before we get into the arithmetic, so we have a plane, right? We have a lattice plane lambda, right? That is spanned by gamma 1 by the charge vectors. And the complexification of that is in H30 plus H03, right? So that's the attractor requirement. Also, we have an orthogonal plane, an orthogonal lattice plane to lambda, right? Under the natural symplectic product of 3 forms. And it satisfies, of course, being orthogonal to that. The complexification is precisely H21 plus H12. So what happens now is that we obtain an isomorphism, right, of H3 with rational, over the rational, giving the sum of these two. But this means that the Hodge structure is splitting, right? So we have a splitting that the rank is, if a rank 2 attractor point exists, that manifold has this property. Its Hodge structure splits over the rationals, right? So this is quite a very strong statement. So I have a rule that never try to say things that I don't understand. So, but so I don't really understand the Hodge conjecture, but we have been told that in fact that the Hodge conjecture says that this splitting must have a geometric origin. So how do we find varieties with rank 2 attractor points, right? We know that we have the Hodge, but the Hodge conjecture is completely useless for this because it's not constructive, right? Doesn't help you. You know that this should exist if the Hodge conjecture is true. So it's a very hard problem, and it is an open question. And we have tried, we haven't succeeded yet. Maybe we'll never succeed, but we don't know. So what we are going to do is to show this splitting first arithmetically. So what we have done is to develop an arithmetic strategy to show this splitting, right? This must have an impact in the arithmetic of the Calabi-Yau. So in fact, in 2019, we actually found, you will see what that means, the first example, and then there were another group soon afterwards found a few more examples, and recently we found a few more, but we don't know what the pattern is. We don't know what given a Calabi-Yau, which ones will have a attractor variety.
What does it mean in physics that there's a rank 2 attractor point?
It means that you do have a black hole with charges, right? It means that you do have a solution for your
Like, how is it different from the rank one case?
So the rank one case, those are in principle. So the rank one case, you have only one charge, right? That will coincide with this plane. In this case, you have two. So if you have a rank one attractor, that doesn't mean you can have a rank two attractor, right? So, and the rank one attractor points are supposed to be dense in moduli spaces, but to this day, we don't understand those less than the rank two attractor points. No. So, so anyway, not to great math. So any questions about this? This was the physics, right? So, and the consequences for mathematics, right? So that there is a splitting of the Hodge structure for these attractor varieties. So let me briefly discuss. This is something I did for you. So now you can relax after the physics. So this should be very familiar, what I'm going to say, but I will say it because I need it. Anyway. So now we will have a family of algebraic varieties, right? So that is algebraic hypersurface with defining polynomial. And normally we work with polynomials over C. I mean, a physicist, we work over the complex numbers, right? So it's very strange for a physicist to start working over the integers or the rationals, even more strange to work with finite fields. But that's what we're going to do. So we are going to work over finite field and compute zeta functions, right? So the fundamental quantities of interest are, of course, the number of solutions over a finite field. And of course, it is well known in mathematics of the last century, right? That there is a generating function, this is the famous zeta function, whose properties are governed by the conjectures and theorems that were proven by Dorf-Delin and Grodendig. So in particular, I mean, Dorf proves that the zeta function is a rational function, and this is true even if your space is not smooth, in fact. So it's right, I mean, what depends on being smooth is what comes next. So this a rational function of, I mean, there are polynomials within the Ri's are polynomials with integer coefficients, and the degrees of each of these polynomials is the ith Betti number, right? And R0 and R2D, R4. So all this is in that context. So for a Calabi-Yau, so I specialized this to a Calabi-Yau 3 for a Calabi-Yau 3. What do the Bell conjectures tell me? Before doing any computations, right? So they tell me that, so for a threefold, we will have R1, R3, and R5 at the top. And then at the bottom, we have, apart from this trivial factor, we have R2 and R4, right? So for a Calabi-Yau threefold, we are taking B1 is 0, B5 now should be 0, and then therefore R1 and R5 are 1. The degree of R3 should be B3, right? And then in the denominator, we have the so the degree of R2 and R4 are the same, are equal, and it's H11. And the nicest cases in which the Picard group is generated by the isosdefined field P R2 and R4 take this almost trivial form. So that's the summary of what I just said. That's for a smooth Calabi-Yau. This is a polynomial of degree. I dropped the 3, right? To alter the notation. So R3 will be for a smooth Calabi-Yau will be of degree 4 for one parameter cases, right? So I'm going to work now, I'm going to specialize to cases in which H21 is 1. So it will be of degree 4, there. And of course, this is well known, right? So the APs and BPs are given by point counts over FP and over FP squared. And then here, this of course the trace of Frobenius, right? So U is the map induced by the Frobenius automorphism on the given topology. But it's the fact that the very hidden here is that all this can be computed from the periods of omega. In fact, the singular case is also very interesting, and is the degree of R now is smaller than 4. So because we want to develop an arithmetic strategy to see when we have an attractor variety. We need, of course, a good computing code to do the point counting. So there are everyone those computational here will have their favorite codes. So we developed our own codes for one parameter cases and for multi-parameter cases. So the fact is that we can compute these R's, which I'm going to start calling them Euler factors at P, right? So we can compute quickly these Euler factors for each phi in P, and of course varying phi varying between 0 and P minus 1, and we can compute it for many primes. So we compute, but before telling you about the computations, let me pause for a second, right? So we have these Euler factors, right? And though we are ready to certain substantial experimentation, I mean, we not just, I mean, a lot of people in the community. So one can ask, what are the properties of these coefficients, right? Of AP and BP, right? So are there many modularity conjectures? There are many conjectures. Is there an analog of the modularity conjecture for elliptic curves for Calabi-Yau triples? And this brings you right into the Langlands program. So we can construct our functions, and we will, right? Which are the products over all the primes of the Euler factors evaluated at P to the minus S. The reason I put it in quotes is because, I mean, to be formal, I will have to tell you what happens at all the at the primes of path reduction, and I have to complete it and so on. But so this equality is not quite right. I think I don't need to explain again to this audience what I mean by this, right? So in the case of Calabi-Yau threefolds, these objects here are called, are called spin or zeta functions of wave 3. So these L functions, I mean, what are the properties of these L functions, right? We don't know. None of this is known. So none is not in general. You might know something about particular cases. So again, so this time, as you know, these are very hard questions. I mean, the modularity is not a classical modularity, right? This for one parameter cases, this is supposed to be a modularity. These are supposed to be these F functions are supposed to be associated to paramodular forms of the Langlands integral of SP4 or something like this, right? So this is very hard. So, but in some special cases, something happens, right? So if you have a rigid Calabi-Yau manifold in which H21 is 0, that means no complex structure parameters, then the degree of R is 2. So it has this form, but there is an AP there, right? And Gouvet and Yue proved that these are all modular, right? So the AP is the Pith coefficients in the Q expansion of a modular form for some congruent subgroup of SO Z. Singularities, I mentioned the singularities before, right? So there are some Calabi-Yau, all Calabi-Yau manifolds at some points in the moduli space develop what pieces for conical singularity. And these are nothing but the singularities are ordinary double points. That's all. And in that case, the Euler factor is of degree 3, right? It has a linear factor and a quadratic factor. This is just a quadratic character, and AP again is the Pith coefficient. So in the Q expansion of the eigenfunction of gamma, right? For the mirror, this is a conjecture. I don't think this is proven, but in many examples this is true. For example, you take the mirror quintic, there is a form with conductor 25, and this was discovered by Chad Shen a long time ago. The Hulle-Campbell family have 3 points in the moduli space where you have these conical singularities. This is not an hypergeometric example, and you do see this phenomenon again. This was their work in the Hulle-Campbell. This is what they wrote up. So to recap, I mean, these APs and BPs, I mean, the point counts depend on phi, and what this time it's hard to say in general what the properties are. There are many conjectures. I mean, interesting things happen for special values of phi, like the conifold and the attractor forces, right? Yeah.
So I have a question. So you were doing stuff with Calabi-Yau's over FP,
Yes.
and then are you lifting to the complex numbers, characteristic 0, or?
No.
I see,
No.
okay.
No, we're doing what the number theories will do, right? With the pound counting and then compute zeta functions,
Okay.
right? And then we compute this Euler factor of degree 4, and you will see what happens
Okay.
to that one. So yeah, so we are working with polynomials over FP.
Okay,
I mean, of course, there's a relation, right, between them, because this point counting is deeply connected to the periods, right? And in some p-adic sense, which is they're closely related to the periods over the complex numbers.
Mhm.
Right? I mean, there is,
Yeah.
but yeah,
What I'm imagining in my head, which is I thought what you're doing is you've got something, a polynomial over Z or something close to it.
Mhm.
You can reduce it to mod P for lots of different P.
yes, exactly. So that's that. Yeah, so we're going to do that. Yeah.
Okay,
So let me go back to the arithmetic of the attractor varieties, right? So recall that for those varieties, the Hodge structure splits, right? So the idea is to look for this splitting in the zeta function, right? So we have R, we have this Euler factor, right? And then what you should be able to observe is that your quadratic factor is split into two quadrics, right? With some coefficients, alpha and beta, and one quadratic factor will be related to the H2112 part of the cohomology, and the other one to H30 to 0.03 part of the cohomology. Of course, this factorization is over Z, and it should happen for all primes, right? For it to be. So, and moreover, because now these are degree 2 pieces, the expectation is that alpha and beta are coefficients of modular forms, right? These are So in fact, by going into the arithmetic strategy, we will get more than we bargained for, not just to see the splitting, but to connect the black hole physics to the arithmetic. So what we did is to make tables, right? We take R, I put back the dependence on the complex structure, for many primes and phi, and look to what we call for persistent factorizations of this factor into two quadrics, right? There was Moore actually conjectured that the values of phi, for which you have an attractor variety, are roots of a polynomial with integer coefficients. That was a conjecture. Luco tells us that this is implied by the Hodge conjecture, but I don't understand the argument, to be honest. So this is what we use this, right? So here, let me give you an example. So for the Fuller-Campbell, right, this table gives you the number of factorizations into two quadrics, right? As phi varies over FP, right? And for example, for P equals 19, you see that the polynomial factorizes 5 times, and I'll show you that later. And you have lots and lots of factorizations, right, at each prime. So this goes from the prime to the prime 300, 600. So we did this until the computer couldn't do it anymore, right? So if you compare this with the mirror quintic, right, something happens that it almost never factorizes. It's a very different Calabi-Yau in that sense. So we that this has no factorizations, whereas this one has 3. So we find with this strategy, right, we find that for the Hurley-Campbell manifold, there is always a factorization when, right, when phi satisfies these equations. So of course, computationally, what you do is that if you accept that these are algebraic, you first you look at factorizations for primes, and then you say, there must be a linear equation you will have a polynomial. You will have a polynomial, right? Let me say G of phi that its roots with integer coefficients, whose roots are the attractor points. Right, and if you find that you have a factorization for all primes, then you say, well, I expect a linear factor in this polynomial, and in fact then you write A You write A phi plus B equals to 0, and you search, right? And then you find that one, and then you take a quadratic, and you find that one. So, and for polynomials of larger degree, we don't expect to find any more. Right. So let me illustrate what happens for p plus 19, right? For p plus 19, phi is congruent to 8. Phi equals to minus 1,7 equals congruent to 8. And phi plus minus is congruent to 4 and 5. Right. So and 17 is a square, right, in that case. So you get that this is an example, one of the tables, right? So we have this for many primes. So here you define factorizations. I mean, you see 3 factorizations for phi plus, phi minus, and phi equals to minus 1,7. Then you have, I said 5, right? So these 2 are not persistent factorizations. So you have to be careful with those. And these 2, these 3 are not counted in the table before. These are the these are the singular, the singular cases, right? In which you have your Euler factor is degree 3 instead of 4. So then you of course you get busy with tables and looking at. But anyway, it was kind of successful. So this is the kind of attractor flow that one gets in the case for phi plus minus 1,7. It's very we produce. I mean, we actually mostly Mohammed produced quite a number of these beautiful flow charts. So the tables have more information. Are there any questions before I go into this? No? Okay. So now we look at the tables where we have factorizations, right? And as I mentioned before, these alphas and betas are supposed to be related to some modular form, right? So this is their conjecture, generalizing the Taniyama-Ba conjecture. This is the motives that to me is I think of motives in these terms, which is probably not right, but that's the moment how it is working. Of length 2 are modular, right?
So what's length 2 mean?
Length 2 means the degree 2. Yeah,
Okay.
yeah, that's the language. It means degree 2. Yes. Yeah. So, and indeed, I mean, we went to the LMFTD website, the functions and modular forms database, and for phi equals to minus 1,7, we found the Fourier coefficients of a modular form gamma 0, 14, right? F2, we have 2 of them because we have 2 quadratic factors, right? We have one modular form of weight 2 and another modular form of weight 4, right? So this is the one that is related to the 3 zeros plus 0, 3 part. So, okay. And for the others, we found modular forms, but now of gamma 1 instead of 34, where this is a reminder of gamma 1. Right? So it's slightly more complicated, but still, I mean, the expectation was that there will be some modular forms, and they are. Okay. So now, what happens at the end, right? Any questions about how I start over mixing physics and mathematics? What do you think about the strategy? So we don't have, whereas we have the computational evidence that we have is so overwhelming in a way, but that it's hard to believe that this won't be true, right? But it's not a rigorous proof. To have a rigorous proof of this splitting or the splitting of the Hodge structure, one will have to find the geometric reason. And we don't have that yet. So we assume that this is true. So this is so we found a two parameter family of black holes, right? In this case, these are the charges. And the area is given, as I said before, as in terms of L values, so the function associated. So L4 is a function associated to this F4, right? So these are the central values of the function, and so this is what we have a metric. We can compute the area of a black hole, right? Of the surface area equals to 0, compute the area, and that's what you get. But in fact, the area is also given in terms of this central charge that I defined before, right? It's the central charge squared, right? That is related to the period associated to the dual of the charge vector. And here we have a black hole entropy, right? So to this day, we're still working on the precise meaning of this, right? Because on the left side, you are counting, you are describing the physics of a black hole. And you're saying that is described by the arithmetic of the Calabi-Yau variety, right? So again, we need to work more on that. So let me show you for the other two.
Oh, sorry, I forgot, what was gamma?
So gamma is the Poincare dual of the charge vector of the charge vector. So again, what's the precise meaning of this, right? So
Sorry, and you said that at this fixed point that modulus of Z gamma phi was maximal or something?
minimum.
Minimal. Okay.
Yes, it also minimum, yeah. So that's right. So this is the other example, right? The 5 plus minus, right? Again, so this lambda here is just a real 5 equal 4, and it's a very similar formula as this object, this star. Right. So what's the meaning of this? I mean, well, for physics, it has an impact, and for mathematics, I mean, we're telling you that this is counting something, right? We're counting enumerative, it's an enumerative question. Right. So these areas, I mean, there are lots of work about the area or the entropy of a black hole, and there are a number of conjectures associated to this. So one can describe this area in terms of a functional that we call the prepotential in physics, right? And so the area is something like the Legendre transform of this area of this functional, right? And the conjecture is that this functional is in fact the logarithm of the partition function of the black hole. And moreover, that is equals to the square of the partition function of a topological strain. Right, so these are very deep. So there should be, let me write it here. So the conjecture, this is a conjecture by Okui, and Strominger, is that the partition function, in the sense that was described in the previous talk, the partition function for the topological string theory square equals the partition function of the black hole. And this is related to the exponential of this prepotential, right? So I could massage these equations and write them in terms of this prepotential, in fact. So this conjecture was very interesting, and it's of course it's true. I mean, we'll relate L values with partition functions, right? But also with a functional. So this is interesting, right? With a functional, this prepotential. So let me now give you another incredible identity that comes from mirror symmetry. Since I have 5 minutes, I will add a word on mirror symmetry. Let me. So mirror symmetry. So a mirror symmetry is a statement that started in physics in the late 80s, right? And says that the quantum field theory, I'm going to call this the quantum field theory of a type 2A theory. So this is some superstring theory, right? That is compactified on a Calabi-Yau X, right? So you have 10 dimensions, and you get, so this is a 4-dimensional theory. I mean, the sense that in the previous, this gives you a 4-dimensional supersymmetric theory that comes from this compactification scheme. should be the same, and it should be three here, to the quantum field theory of the type 2B, which we have been discussing on let me change this to Y. And its mirror. So Y is the mirror of X, the mirror of Calabi-Yau. So as I said that the Calabi-Yau and its pair, I mean, they come in pairs and they have interchanged their Hodge numbers, but there are more properties, right? So this equivalence is an equivalence again of partition functions, and it is not a classical relation at all. I mean, you have to consider your theory and all the quantum corrections. I mean, all the correlation functions will be equal, including the quantum corrections. It's a very, very strong statement. And the mathematical statement, the equivalent statement in mathematics is an equivalence of categories, right? Which I won't try to repeat, but that's what happens. So baby versions, not talking of categories or anything like that, is that the moduli space, the moduli space of the complex structure of X, well, should be isomorphic to the moduli space of the Kähler class of its mirror. Right? The dimension of this one is, the dimension of the first one is H21, and the dimension of the second is H11. The complexified dimension is H11. So, and the isomorphism map is called the mirror map. Right? So if you have complex structure parameters here, so these maps find phi of these, and this is the mirror map. And this can be, again, computed using periods. In fact, the mirror map is as I have here, the mirror map, I have right? It's given by, it's a rational function of the periods of the Calabi-Yau. So one can write down the periods and then construct the mirror map, the isomorphism map, which is this map that I have. So then the question is, what is mirror symmetry doing to this, to what I described, right? So I describe an attractor mechanism on this side, right? So what is it on the other side? And then you can, in fact, actually describe it again and solve the equations. And on the side, on the complex structure side, you don't see this, you see periods, right, all the time. On the other side, what you see is a classical theory with quantum corrections, and the quantum corrections in mathematics are the Gromov-Witten invariants, for example. So what you find is that you find these beautiful identities of these sorts. So on the left-hand side, here, you have a number given in terms of L values, and this here is proportional to the value of the Kähler class parameter of the mirror at the attractor point phi minus, right? That's precisely that number, also given in terms of L value. It comes from this equation, right? So the left-hand side, that's what you have. So this is the solution to the attractor equations in the type 2A side, if you like. And of course, on the right-hand side, and this is also proportional to the area of the black hole as the formula that we saw before, right? So in the type 2A, that looks like an incredible identity on the right-hand side that involves the Gromov-Witten invariance. So what is being conjectured is that we're not the first ones to say that, right? That areas of black hole are related to Gromov-Witten invariance. This is, in fact, somehow in the conjectures by and Baffa. Right. So L values here are related to this counting here. So perhaps this might be getting closer to relating this area to precisely an enumerative problem, right? So I think we find this quite interesting. I mean, this was first pointed out in 1921 by Philip and our two students, Joseph McGovern and Puru Kusela, who are now postdocs. And as you saw before, I mean, they collaborated with us in what happened after this work. And so recently more identities were presented together with Joseph for other examples and that are more complicated, but you still have this relation, right? So with that, I would like to finish. question is. And just an outlook. So I already said, I mean, what the big questions are, right? I should repeat this. So, thank you for listening and happy birthday to Mignon and best wishes for many, many more.